Good afternoon, everyone. My name is David Ecotier from the Joint Research Unit in Environmental Acoustics in France. This talk deals with new developments about noise mapping methods. We present here a new approach for city noise map production and also a sensitivity analysis of noise map results to noise model inputs. This work also involves Gustave Eiffel University, who led the project, and CNRS, who contributes to this research. The research was funded by the French National Research Agency, CEREMA, Gustave Eiffel University, and CNRS. The global context of this research is the urban noise mapping that is required by the European Directive on Environmental Noise. The relevance of noise maps for large cities is sometimes questionable because of poor quality or insufficient accessibility of input data and the large number of input parameters. To address this issue, the CENSE Project aimed at proposing a new methodology for the production of more realistic noise maps based on an assimilation or simulated data and measured data. In the framework of this project, a specific work package was dedicated to access to enhanced input data in order to a priori reduce uncertainties, and next to study the relative influence of all those varying parameters on the final and global uncertainty on the noise prediction. Collecting input data for noise mapping is often a difficult task, and obtaining good quality data is certainly even more difficult. A specific process for noise mapping is presented here, based on the coupling between an open source noise mapping software and an open source spatial database that can provide most of the input data for noise mapping. The noise prediction method we used for road traffic noise is the European method CNOSSOS EU that is required by the European Directive. This method was implemented in noise modeling, an environmental noise prediction software developed by the authors. Noise modeling is based on the Geographical Information System, or BISGIS. It is open source and freely available on the net. It can be used as a Java library or through a web interface. The full implementation of CNOSSOS EU was part of this work package. Noise modeling can accept input data as buildings, topography, and so on in different ways. The most common way is to use data from any available classical database. An alternative way is to use open data. A specific process has been developed to use OpenStreetMap data for noise modeling thanks to Groovy scripts to manage interactions between noise modeling libraries and a special database for getting most input parameters. All data coming from OpenStreetMap are requested, processed, and formatted by means of the open-source geospatial toolbox GeoClimate. Data are organized as a series of GeoJSON files in the form of attribute data from several geoclimate layers. Noise modeling requires at least 3 geographical layers to be able to predict noise levels. Buildings with location and height information, ground with category of the ground and information about the vegetation. Ground information are useful to estimate the ground impedance coefficient required by the propagation model. And finally, the roads layer is also necessary in order to access to vehicle traffic and pavement type information. The European Good Practice Guides gave the association between OSM information and the CNOSSOS EU model requirements concerning the road type and category that are used to estimate road traffic information and the road pavement. To validate the new process we developed, OSM-based noise predictions were compared with the reference noise map of 5 districts of the city of Paris. The so-called reference map is the noise strategic maps calculated in the framework of the European Directive using the commercial software CADNA. The errors made on noise levels prediction are calculated with the deviation between sound levels of the two maps at some receivers sampled randomly in the map. An example of these results are given here, which enable to compute distribution of errors of Elden estimates. And we also made a comparison for L-night estimate. Finally, we found that OSM-based noise maps tend here to overestimate sound levels compared with the classical method. About 75% of sound levels deviations between the two methods are between 2.5 and 7.5 dBA for L10, whereas it is 64% for L-night. Even if everything is not explained yet, a first explanation is likely to be the difference between road traffic data between the two methods. While classical method uses real road traffic data, the OSM use the good practice guide to estimate it from road information. Empirical laws between traffic and kind of roads might be too rough or not adapted to French road traffic. The quality of input information has not the same importance according to each input parameter. We present here the main results of a sensitivity analysis of noise mapping results in order to assess for which parameters it is crucial to have input information of good quality and for which ones raw information are sufficient. For this, we used the Morris method that is widely used for global sensitivity analysis. The process consists in exploring the parameters domain to vary the inputs one at a time and to repeat it randomly in the parameters space, where each input parameter interval is discretized into a suitable number of levels. The method starts by sampling a set of initial values within the defined ranges of possible values for all input parameters, and by calculating the subsequent model output. The second step changes the value of only one parameter and calculates the resulting change in a model output compared to the first result. Then the value of another parameter is changed and the resulting modification in the model outcome compared to the second run is calculated. This goes on until all input variables are changed. The process is repeated several times with multiple trajectories. The influence of each parameter can finally be quantified through several indices that will be described in the next slide. The advantages of the method are a reasonable cost compared to the number of parameters, the possibility to attribute changes to each input, and to estimate the possible presence of a cross effect. 3 indices are calculated with the Morris method to quantify influence of parameters on the output. The mean value of the effect, the mean value of absolute effect, and the standard deviation of the effect. All these indicators can be calculated for each parameter. We applied the method to noise mapping. The sensitivity analysis is performed here following the CNOSSOS EU method for road traffic noise that is implemented in noise modeling. More than 40 input parameters can be identified when calculated a noise map using CNOSSOS EU, but only some of them are prone to generate significant uncertainty on the output. The proposed sensitivity analysis focuses on 15 input parameters, among which 4 concern the model configuration and 9 are related to physical inputs. 3 outputs are investigated: L10 at each receiver, L10 value average on the map, and population ratio exposed above 65 dBA. The sensitivity analysis presented here uses the case study of the CENSE Project, that is the city of Lorient in France. It covers an area of about 2 square kilometers, with more than 14 receivers for more than 1,000 buildings. The influent input parameters are a compilation of data collected from CERMA, IGN, and the Lorient City Council. Here are the main results. Parameters likely to impact the ratio of inhabitants exposed to levels above 65 dB are especially those influencing the calculation for receivers at level close to 65 dBA. The most influential parameters in this study are a propagation parameter, that is the horizontal diffraction, and two source parameters, the vehicle flow rate on medial axis and the ratio of heavy vehicles. In terms of the mean Haldane value, the most influential parameter is by far the horizontal diffractions, which leads to a variation of 3 dBA of the mean Haldane value in this study. This is because some receivers which are not in direct field with the sound sources are not reached by any propagation path if diffraction is ignored. This concerns a limited number of receivers, but it makes the mean of the absolute effect jump to a high value. To conclude, this research presented some improvements of urban noise mapping process by exploring two aspects. The first one dealt with input data and noise mapping process. We proposed a specific process for noise mapping based on the coupling of an open source noise mapping software, that is noise modeling, with an open source spatial database that can provide most of the input data for noise mapping. The comparison between an OSM-based map and a reference map for a part of Paris City validated the feasibility of the approach. It nevertheless showed some deviation for both Haldane and L-night noise levels, which are probably due to road traffic data used for the OSM-based map, estimated for the road type, and using the empirical laws given by the good practice guide that might not be adequate in this case. The second aspect dealt with the relative influence of input data on noise mapping results. The Morris method we used showed that horizontal diffraction is the most influential parameter for both estimate of population ratio exposed to more than 65 dBA and on mean Haldane, and that vehicle flow rate and medium axis and a ratio of heavy vehicles are also influential in the case of exposed population. Thank you for your attention.